Welcome. This presentation is based on the article Measuring Station for Testing on Ear Headphones, made by 3D printing used in Industry 4.0 inches by Pekold, Blazejewski, Krolikowski, Trzebiatowski and Fialek from Koszalin University of Technology in Poland. This work focused on creating and testing a station that could evaluate the performance of headphones, especially how different materials inside the acoustic chamber affected the sound quality. Particularly, the study aimed to design and then build a test station to measure the characteristics of headphones, where the effect of different acoustic materials used for filling the acoustic chamber was investigated. In this presentation, it will be told about how is measure the acoustic performance of commercial earphones using a custom-designed test station. It will be also shown how artificial neural networks can be used to predict the filter attenuation of different earphone models based on the test station data. The presentation will cover the following topics: introduction, some commercial earphone acoustic measurement stations, test station design, research using the test station, filter attenuation prediction using artificial neural networks, and results obtained. Over-ear, on-ear headphones, as we know them today, first appeared in 1910. The drivers, loudspeakers, used in them have changed over the years. Magnetostatic, piezoelectric, electrostatic, and, the most popular nowadays due to lower production costs, dynamic transducers have been used. Over-ear, on-ear headphones can be divided into two basic types due to their construction: open back and closed back. Closed back headphones are generally considered more difficult to design correctly. A common problem is the impulse response with a long fade-out time. Every year, there are many tutorials on the Internet audio equipment forums on reducing reverberation at home or optimizing the frequency response of a particular headphone model. It is often a matter of filling the acoustic chamber with a specific material. This way, the reverberation phenomenon can be reduced, and, depending on the material used, the frequency characteristics of the headphones can be altered. Some companies on the market, such as the American Lawton Audio or the Polish Shipibo Audio, specialize in modifying the acoustic chambers of headphones. The popularization of the phenomenon has prompted an investigation into the effect of different, frequently used materials on changes in the sound generated by headphones. A better understanding of these relationships would allow manufacturers to use more suitable materials at the design and production stages. Various test stations for over-ear headphones are used to check and evaluate their acoustic performance. Depending on the parameters of the headphones being tested, the following can be mentioned. 1. Frequency response test station for measuring the frequency response of headphones. Such a device consists of an audio power supply unit, an amplifier, a sound generator, a microphone, and a suitable sound analysis system, usually in the form of a computer application. 2. Acoustic isolation test station for measuring the ability of headphones to isolate external sounds. Such a device consists of an artificial head, a phantom with internal and external microphones, a noise generator, and a computer with a suitable application. 3. The delay time measuring station is just for measuring the delay time between input and output signals. Such a device usually consists of a signal generator, amplifier, microphones, and oscilloscope. 4. Harmonic distortion test station for measuring the harmonic distortion level of sound headphones generate. Such a device comprises a signal generator, amplifier, spectrum analyzer, and microphones. 5. Sound pressure level measuring station for measuring sound pressure levels in headphones. Such a device consists of a sound generator, amplifier, sound level meter and microphone. 6. Power level test station for measuring headphone output power levels. This device comprises a signal generator, amplifier, power meter, and microphone. The object of this paper is to present the author's low-cost design of a test station and, as a demonstration of its functionality, to investigate the effects on the characteristics of headphones of different materials filling their acoustic chamber. An essential aspect of the project is the application of incremental manufacturing methods, such as 3D printing, which is used in many aspects of the manufacturing process. The main problem posed by the station's functionality is, in this article, a comparative analysis of the characteristics of headphones after using different materials as acoustic chamber filling. The work can help to select the optimum design solution when modifying an existing model or assist at the design stage of future products. Measurements of the headphones should be taken under conditions as close to in-use conditions as possible. Two typical methods of measuring headphones are the application of a so-called artificial ear and a binaural microphone in the form of a HATS, head and torso simulator, the head itself, or a head section of the auricle and ear canal area. One artificial ear. An artificial ear is a device that geometrically and acoustically mimics the human middle and outer ear. The artificial ear merely approximates the acoustic conditions found in the actual ear. It does, however, ensure stable measurement conditions. The essential component of the artificial ear is the coupler, an acoustic chamber that simulates the ear canal. The leading and probably most recognizable brand in the production of the artificial ear is Brüel and k23 binaural microphone. The first to appear on the market were expensive stations used mainly in recording studios to simulate the whole head, such as the Neumann KU-100, costing around PLN 40,000. They were initially used for binaural recordings, where the listener can pinpoint the acoustic signals recorded in space. It gives the impression of being in the place where the recording was made. Below is a photo of a Neumann KU-100 microphone. Later on, cheaper equivalents that only represent a section of the head with the auricle and ear canal, such as the 3DO free space binaural microphone, became popular. Because of their relatively low prices and compliance, such microphones began to be used to test the properties of headphones. Acoustic measurement software environments that enable acoustic measurements can be divided primarily into those with dedicated test stations and those that work with any USB interface or sound card. These are primarily commercial and professional programs. They are characterized by frequent updates, outstanding support, and a multitude of functions. Native software for their products is being developed by Audio Precision and GRA, among others. Still, the most popular and extensive of the packages of this type is Clio 12, developed by the Audiomatica company. The set has a vast range of functions. In addition to the basics, that is, the ability to examine frequency and impulse characteristics, it can examine harmonic distortion and THD, create a CSD waterfall type 3D plot and perform detailed fading analysis. The undoubted disadvantages include the need for a dedicated test station, and the cheapest set enabling any measurements available in Poland costs around PLN 3,000. Below are the characteristics measured with the application. Immensely popular, but with minimal features, is the free Rightmark Audio Analyzer app. Its greatest strengths include simplicity and clarity, but the small number of functions and poor application refinement prompt the search for an alternative. The illustration of characteristics measured using Rightmark Audio Analyzer. Room EQ Wizard is a free application that does not require dedicated hardware but is much more extensive and refined. The first stable version of this program was made available in 2005. Initially developed to measure room acoustics, it has been extended over time to include new functions. The undoubted advantages include a straightforward interface, seamless compatibility with studio interfaces, and many functions. Apart from essential functions such as the measurement of frequency and impulse characteristics, it enables creating CSD waterfall type 3D charts for the characteristics like paid applications. A sound generator is also integrated into the application, as well as several functions that are useful for comparative analysis of multiple charts, such as the collation of multiple characteristics and a wide range of color and filter selections. The rich functionality, transparency and refinement, the possibility of free use, and an extensive database of information about the software were the reasons for choosing it during the study. The test station consists of a computer with Room Equalizer Wizard software installed, a Behringer Euphoria UMC22 studio interface connected to it, and a binaural microphone with headphones. The diagram below shows the layout of the test station, Figure 1. To reliably measure the characteristics of the headphones, it is necessary to provide them with conditions similar to those in use, that is, microphones placed inside the headphone channel and pressure of the headphone pads against the surface head, to avoid a drastic drop in sound pressure. Binaural microphones are ideally suited to the premise of headphone characteristics testing. The body for the microphone was the open binaural project shown below, made available for free under an open license by author Carlos Garcia Sora on github.com. The authors has rendered the shape of the ear canal quite faithfully and provided space for the microphone capsule. The microphone capsule was fixed in the channel with silicone and then flooded for extra insulation on the pin side with polyamide glue, which is used for electronic circuits. Panasonic WM61A microphone capsules were used. Due to their exceptionally even characteristics, it is a generally recommended model for all measuring stations. The design was made using 3D printing technology. A universal camera tripod was also used as the base. The finished microphone is shown in the photo below Figure 2a. The microphone requires power and the ability to transfer data to a computer. Studio interfaces with an integrated microphone amplifier, such as the Behringer Euphoria UMC22, Figure 2a, are ideal for that purpose. The interface also provides a signal source for headphones. The headphones used, Figure 2b, are based on the Denon RD5000 driver. The acoustic chamber is made of Indian lilac wood by Artisan Audio Lab, and the leather pads were made by Lawton Audio. The materials studied was selected through consultation with Shipibo Audio, a Polish company involved in modifying the acoustic chambers of headphones, and by following headphone modification topics on the largest English language online forum on audio equipment, headfeed.org. 3 different materials were selected for the study: silicone non-woven, Figure 3a, used, for example, in the production of sound-absorbing coverings and in the clothing and furniture industries; cotton wool, Figure 3b, used, for example, in the production of the very popular cosmetic swabs. 3. Ceramic fiber, Figure 3c, used as a high-temperature insulator. Measurements are taken in a place as quiet as possible to reduce external interference. A microphone calibration was carried out before the measurements. Each measurement was taken 3 times after the headphones were removed and put back on the microphone. First, background measurements were taken, as seen in the graph, Figure 4. The characteristic peak at 50 Hz is probably due to the operation of equipment using voltage converters. Afterward, measurements were taken without filling the acoustic chamber, as a reference for subsequent tests. Next, the headphones were disassembled, the acoustic chamber was filled with the test material, the whole set was assembled, and the measurements were repeated. The voltage, volume potentiometer, of the sound source was set so that the reading or the sound pressure generated by the headphones without the acoustic chamber and filled and recorded on the binaural microphone did not exceed 85 dB. This sound pressure value represents the conventional limit of damage to hearing. The volume on the sound source was not changed in any of the subsequent measurements. The measurement was made in the human audible frequency range of 20 Hz 20 kHz, and the time of a single frequency response measurement was set to the maximum length provided in the software, that is, 23.8 seconds, for the most accurate readings possible. In the case of the impulse response measurement, a white noise pulse of a very short duration was sent. First, measurements were taken without filling the acoustic chamber, Figure 5. This measurement will serve as a reference for further measurements, assuming filling the headphone's acoustic chamber with damping material. The graph below Figure 6 shows that the sound pressure drop is relatively linear over the entire range tested. It is slightly higher in the bass and mid-range, 20 Hz 3 kHz, than in the treble, 3 kHz 20 kHz. In this graph, Figure 7, we can observe an even more significant drop in the bass range and partially in the mid-range, 20 Hz 600 Hz, while the rest of the band has been reduced by a similar amount to that of the silicon fiber filling. In the last graph, Figure 8, in the case of the ceramic fiber filling, we notice a large drop in the 20 Hz 400 Hz range, similar to that of the cotton wool filling. There is a greater drop in the treble range, 3 kHz 20 kHz, than for the other 2 materials, and for the remaining characteristics, the drop is similar to that measured when the chamber is filled with the other materials. The diagram, Figure 9, summarizes all frequency response measurements. Unfilled, pink; filled with silicon fiber, green; filled with cotton wool, blue; filled with ceramic fiber, red. The effect of the acoustic chamber filling material used on the frequency response is noticeable. In the 400 Hz 3 kHz range, the changes in response for each material are similar. The greatest differences can be observed in the 20 Hz 400 Hz range. The 20 Hz 100 Hz range has the highest noise. The characteristics coincide with information obtained from the Polish company Shipibo Audio and online forums on audio equipment, where a weakening of low frequencies with cotton wool and a prominence of mid-range frequencies with ceramic fiber were described. The graphs show a drop in sound pressure in the bass and treble. The chart, Figure 10, confirms the effect of the acoustic chamber filling material on the time of impulse characteristics: fading, unfilled, pink, filled with silicone fiber, green, filled with cotton wool, blue, filled with ceramic fiber, red. The longest characteristics fade-out time occurs when there is no filling. After the use of silicone non-woven, the time was slightly reduced, 8 ms, with cotton wool, 7.5 ms, and glass fiber, 7 ms, having the shortest pulse fade-out time. Based on performed frequency characteristics examples figure from 4 to 9, and impulse characteristics, example, figure 10, an artificial neural network was built, whose task is to predict the headphones with filter damping properties. This feature has significant influence on the sound quality headphones generating. The above-mentioned measurement results were used to train the network to find a regression function describing the relationship between frequency and impulse characteristics. A network was built based on the input and output fitting problem with a neural network toolbox in the MATLAB environment, where 1. Input data net predictors is the set of 11x16 size and target data net responses is the 1x16 size set 11 features, SPL, that is sound pressure level, dB, for selected frequencies of the frequency characteristics, were chosen in the teaching process. Central frequencies, 50-5000 Hz, was selected from the characteristics. The network response is the sound decay time corresponding to the attenuation properties of the filter. 2. Training function was chosen in the forms of unsupervised random order weight bias functions, Bayesian regularization. 3. To create a fitting network, after searching the best hidden layer size, 5 were chosen finally. Higher layer size did not improve the results for the input and output pre- and post-processing in the forms removing matrix rows with constant values and map matrix row minimum and maximum values to -1, were chosen respectively. 5. The division of data for training, validation and testing were chosen in following amount: 70%, 15% and 15% respectively. 6. The performance function was chosen as the mean squared error. This resulted in the following network structure, Figure 11a. The results in form of regression functions were obtained after reaching minimum mean squared error criterion. It was done in 39 epochs, Figure 11b. The following regression functions, Figure 11c, were obtained after reaching minimum mean squared error criterion. From the collected data, it can be seen that using any material to fill the acoustic chamber of the headphones leads to a drop in sound pressure. In the low frequency range, 20 Hz 300 Hz, and almost the entire mid-frequency range, 300 Hz 3 kHz, the sound pressure drop of approximately 5 dB occurring when using silicone non-woven. For cotton wool, it is 15-10 dB in the low frequency range and 10-5 dB in the mid-frequency range. For ceramic fiber, the sound pressure drop in the low frequency range is slightly higher than that in the case of cotton wool, and exceeds 15 dB. At 400 Hz, the values equalize and, for most of the mid-range, the attenuation of the ceramic fiber is less than that of the ceramic wool. The situation changes from the upper mid-frequency range upwards. The sound pressure drop for silicone non-woven and ceramic wool becomes equal and is less than 5 dB, but for ceramic fiber it is greater and exceeds 5 dB. At high frequencies, 3 kHz 20 kHz, the sound pressure drop is smaller than at low frequencies. In the case of silicone non-woven and cotton wool, these values are below 5 dB, but ceramic fiber causes a noticeably greater drop, exceeding 5 dB. It means that the use of silicone non-woven leads to a similar degree of sound attenuation across the entire frequency range audible to humans. In the case of ceramic wool, the attenuation is significantly higher in the low and mid-frequency range. Ceramic fiber, on the other hand, has the strongest low and high frequency attenuation properties, but at the same time has the weakest mid-frequency attenuation in the 400 Hz 2 kHz range. The shape of the binaural microphone proved to be the biggest problem during testing. The inclination in the plane around the auricle as compared to commercial solutions was too large. This, combined with the rigid plastic of which it was made, translated into a poor fit between the headphone pads and the microphone, resulting in a drop in sound pressure. This resulted in a lower than actual sound pressure being recorded, mainly in the low frequency range. However, the test consisted of comparing the characteristics using different acoustic chamber filling materials, and as the lack of tightness caused a pressure drop in each measurement, this did not significantly affect the test as a whole, and it was possible to see differences in this frequency range as well without any problems. Obtaining suitably quiet conditions for the measurements was also a problem. The best solution would be to carry out the measurements in an anechoic chamber or a very acoustically insulated room. Because of the lack of access to a suitable room, the measurements were carried out at night due to the lower values of the recorded background noise. Due to the growing interest in the high-end audio products among users and the emergence of numerous companies manufacturing or modifying headphones, investigating the acoustic properties of the materials used in production appears to be crucial to designing commercially successful models. The primary aim of the research was to determine the effect of different materials filling the acoustic chamber of over-ear headphones using a custom-built and printed test station and, using a computer program, to make measurements of the frequency characteristics. The research has shown how much influence just one of the many elements of headphones can have on their final characteristics. The measured characteristics made it possible to draw conclusions and revealed certain trends. A definite effect of the acoustic chamber filling material on the frequency response of the headphones was observed, different for each material. Due to the shape of the test station, too much inclination of the plane around the auricle, the tests proved problematic, but this did not prevent measurements of characteristics and comparative analysis. The significant differences in frequency characteristics confirmed the importance of knowing the acoustic properties of materials on the headphone design process. The greatest differences in characteristics with the different materials were noted in the low and high frequency ranges. Silicone non-woven reduced the sound pressure over the entire range to a similar extent and resulted in a smaller reduction in the time of impulse characteristics fade-out than the other materials. Cotton wool resulted in greater reductions in sound pressure values in the low 20 Hz 300 Hz and mid 300 Hz 3 kHz frequency ranges, and comparable to silicone non-woven in the high one. It also caused a faster fade-out of the impulse characteristics than the silicone non-woven. Ceramic fiber had the highest attenuation of the low and high 3 kHz 20 kHz frequency range, but at the same time the lowest attenuation of the mid-frequency ranged from 400 Hz to 2 kHz of the three materials tested. The fade-out time of the impulse characteristics was the shortest. Information on the effect of individual materials on the characteristics of the headphones overlapped with that obtained from the Polish company Shipibo Audio at an early stage of information gathering. Thank you for your attention.